Here is a real test from OpenAI's HumanEval benchmark. The function must return true when any two numbers differ by less than the threshold. So the first test returns false because its smallest difference is 1.0, which is not less than 0.5, while the second test returns true because 0.2 is less than 0.3. If the condition used greater than instead, the first test would return true and fail. So now focus on the point in the code just before this condition. During standard language model training, the model uses only the code before that point to predict one correct target, the next token, but could we also train the same point to predict several correct tokens farther ahead while keeping those later tokens hidden from the model? That change is called multi-token prediction, and to understand it, we first need to see exactly what next token training measures. At the code position we just marked, standard training asks which token comes next after the code the model can already read. A tokenizer converts the code into ordered token IDs, and shifting a copy of 10 IDs by one position creates 9 pairs, with each position aligned to the ID that follows it. At position t, the model receives only x1 through xt while the later IDs stay blocked, so xt plus 1 can be the known target without becoming an input. The model assigns a probability to every possible next ID, and the target selects the probability for xt plus 1, whose negative logarithm gives the loss at position t. Training knows the complete sequence, so one causally masked pass calculates all 9 losses together, while each position still uses only its allowed prefix. Generation has no later IDs, so the model must predict one ID, add it to the prefix, and run again to predict the next. Next token training therefore measures many positions at once, but each position has only the immediately following ID as its target, which raises a direct question about what changes when later targets are added to that same position. At this position, the visible prefix and input boundary remain unchanged, every later token stays blocked from the input, and the model processes the prefix once. The existing output uses the result to predict xt plus 1, and 3 added outputs use the same result to predict xt plus 2 plus 3 and plus 4. So these 4 outputs are prediction heads, and training them together is called multi-token prediction. Each known future token selects the probability assigned to it by its matching head, which creates 4 losses at this position, and training sends all 4 losses back to their heads and the shared model. These are separate predictions for fixed future positions because no prediction becomes input to the next head, so the 4 outputs do not by themselves form one generated continuation. In a 4-token segment, the first position has 4 target losses, the next has 3, then 2, then 1, which gives 10 lost terms without claiming 10 times the compute or performance. DeepSeek v3 uses a sequential training variant in which the correct preceding token enters the next prediction stage, but it still adds a loss for a farther target. So the next question is whether these additional losses improve the trained model. We can now fill the empty plot with models trained at the same total parameter count, where multi-token training often scored lower at smaller tested sizes and higher at larger sizes from 300 million to 13 billion parameters. At 13 billion parameters, the multi-token model solved 12% more HumanEval problems and 17% more MBPP problems than the matched next token baseline, and both numbers are relative increases. In a separate 7 billion parameter test of 1, 2, 4, 6, or 8 targets, 4 produced the highest HumanEval and MBPP pass at 1 scores, which measure the percentage of problems solved with one generated answer, while 6 was favored on several APP's measures, so the best count depended on the benchmark. Equal parameter counts came from moving layers from the shared model into the extra prediction heads, and the 4-target implementation took 1.22 times as long to train, which the authors attributed to implementation overhead. These results show that multi-token prediction can improve code benchmark scores under some tested conditions, but they do not show that more targets always help or that generation becomes faster, so we now need to test the extra predictions during inference. Those 3 translucent tokens are drafts, so none can enter the output until the ordinary next token model checks them. For greedy decoding, one target model pass checks the whole proposed block, where the first check uses only the accepted prefix, and each later check also uses earlier drafts. Starting from the left, consecutive matches are accepted, but at the first mismatch, the target token replaces the draft, and every later check is discarded because it used the rejected draft. This operation is greedy speculative decoding, and if all 3 drafts match, one target pass can commit 3 tokens instead of requiring 3 sequential target passes, although draft computation and verification still take time. One 7 billion parameter experiment with 3 drafts reported 3.0 times baseline speed on code and 2.7 times on text, with 2.5 of the 3 drafts accepted on average for code, while DeepSeek v3 reported 85 to 90% acceptance for 1 extra token and 1.8 times as many output tokens per second in its serving system. These measurements come from different systems and are not directly comparable, but both keep every committed token under the target model's control. Back in the code where we began, 2.8 and 3.0 differ by 0.2, which is less than the threshold of 0.3, so the condition must use the less than operator and the test returns true. Multi-token prediction does not guarantee this operator because training keeps the standard next token loss and adds losses for later targets that remain hidden beyond the input boundary. During generation, the extra predictions can become drafts, but the target model checks the block, accepts only consecutive matches from the left, and supplies the token at the first mismatch. Reported experiments found higher code benchmark scores for some models trained this way and faster generation for some verified draft systems, but these are separate results from specific tested settings rather than guaranteed outcomes for every model. Multi-token prediction therefore keeps the same input at each position and adds losses for several future targets, while any extra prediction used during generation remains a draft until the target model approves it.